This research paper introduces an adaptive generalized neural network, AGNet, for ship-radiated noise recognition. The proposed system is designed to enhance the generalization ability of features by adopting a learnable fine-grained wavelet transform and a parallel convolution attention module. The end-to-end system includes data preprocessing, wavelet-based feature extraction, and an attention-based classifier. In the data preprocessing stage, audio signals are obtained through array signal processing and transformed into two-dimensional spectrograms by wavelet transform. The classifier then receives these spectrograms and outputs the classification results. The learnable fine-grained wavelet transform allows for differential analysis of frequency bands, which is crucial for underwater acoustic signals where information varies greatly across different frequency bands. This transform also enables the adaptive learning and updating of parameters during training, making the recognition model more suitable for practical application scenarios. The parallel convolution attention module is added to the neural network to focus the attention of the network on valid time-frequency domain information in spectrograms. This module utilizes depthwise separable convolution structure to reduce parameters and enhance the efficiency of the network. Experiments show that AGNet achieves satisfactory recognition accuracy on 3 underwater ship-radiated noise databases: Seashore, 85.48%, Deep Ship, 77.09%, and data collected from Thousand Island Lake, 95.76%. The adaptive generalized network maintains excellent performance even with low signal-to-noise ratio or low cutoff frequency. Moreover, AGNet benefits more from transfer learning due to its more learnable parameters, making it robust against high background noise and low cutoff frequency. The research focuses on adaptive ship-radiated noise recognition using a learnable fine-grained wavelet transform. It introduces a novel approach by transforming traditional wavelet transforms into learnable ones, allowing for adjustable time-frequency resolution. The learnable wavelet transform is applied through the AGNet, which automatically learns optimal wavelet parameters. This is achieved by converting wavelet parameters into learnable ones, enabling the wavelet basis at different center frequencies to learn differential parameters in a data-driven manner. The approach is particularly effective for underwater acoustic signals characterized by high background noise and low frequency content. The study utilizes 3 wavelet basis functions commonly applied in underwater acoustics: complex Morlet, complex Shannon, and complex frequency BSP line wavelets. The AGNet's architecture includes an attention-based ResNet classifier, which enhances recognition by focusing on informative parts of the signal. The training process involves feeding raw audio sequences directly into the AGNet, converting them into wavelet spectrograms, and then using these spectrograms for recognition. This innovative approach demonstrates significant potential for improving ship-radiated noise recognition in underwater environments. Here is a combined summary of pages 5 and 6 of the research paper. This research focuses on adaptive ship-radiated noise recognition using a learnable fine-grained wavelet transform. The authors merge 9 vessel types into 4 experimental classes and 1 background noise class based on vessel size. The experiment setup involves 3 datasets: ShipSeer, Deep Ship, and DTIL, which are preprocessed by downsampling to 16,000 Hz and cutting into 30-second segments with 15-second overlaps. The authors use 4-fold cross-validation to ensure credible and persuasive results. The authors experiment with various feature extraction frontends, including time domain features, MEL filter banks, VGISH, STFT spectrogram, Gabor spectrogram, and wavelet spectrograms with fixed and learnable parameters. The results show that learnable wavelet spectrograms outperform other feature extraction methods, achieving better and more robust performance. The authors attribute this to the adaptive resolution of wavelet transform in the frequency domain, which is beneficial for the recognition task. The authors also analyze the influence of different wavelet basis functions on the results, finding that the complex frequency BSP line wavelet, FBSP, performs slightly better than others. They visualize the learnable parameters, revealing that AGNet tends to learn significantly different parameter values on the 3 datasets. The learned parameters on ShipSeer and DTIL are similar to the inverse DFT, while on Deep Ship with complex background noise, the parameters fluctuate wildly. The authors conclude that the learnable fine-grained wavelet parameters play a positive role in the recognition system, allowing the model to adapt to different sources of underwater acoustic data. They also find that the flexible learning of wavelet parameters makes it possible to draw more informative spectrograms when processing complex underwater acoustic signals. Adaptive ship-radiated noise recognition with learnable fine-grained wavelet transform. This research paper presents a novel approach to ship-radiated noise recognition, leveraging an adaptive, learnable fine-grained wavelet transform for enhanced time-frequency domain analysis. The proposed model, AGNet, utilizes parallel convolutional attention blocks to automatically adjust the resolution of the time-frequency domain based on the input data. This adaptive feature significantly improves the model's performance in recognizing various ship types from their radiated noise signals. In the experimental section, the authors compare AGNet with two baseline methods: MEL filter banks and fixed wavelet spectrograms on three datasets: ShipSeer, Deep Ship, and DTIL. The results show that AGNet outperforms the baseline methods in all datasets, demonstrating its effectiveness in ship-radiated noise recognition. The paper also explores the role of attention blocks within AGNet. An ablation study reveals that adding attention blocks to the model can further enhance its performance, particularly when utilizing learnable wavelet spectrograms. This indicates that the attention mechanism plays a crucial role in refining the model's ability to differentiate between various ship types. Furthermore, the authors conduct experiments on transfer learning, pre-training AGNet on a large-scale audio dataset called AudioSet before fine-tuning it on underwater acoustic recognition tasks. The results show that transfer learning significantly improves AGNet's performance, especially for learnable wavelet spectrograms. This suggests that the knowledge learned from the audio domain can be effectively transferred to the underwater acoustic domain, enhancing the model's convergence and performance. The paper also evaluates the robustness of AGNet against various interference factors, such as low signal-to-noise ratios and high cutoff frequencies. The results indicate that AGNet is more resilient to these challenges compared to baseline methods, thanks to its adaptive wavelet transform and attention mechanism. Overall, this research introduces a novel approach to ship-radiated noise recognition, leveraging adaptive wavelet transforms and attention mechanisms to enhance the model's performance. The proposed model, AGNet, demonstrates superior performance compared to baseline methods and shows promising results in practical applications, particularly when dealing with interference factors. This research proposes an end-to-end ship-radiated noise recognition system, AGNet, which leverages a fine-grained wavelet transform and a CNN-based classifier with parallel convolution attention blocks. The system achieves promising recognition accuracy on three datasets: ShipSeer, 85.48%, Deep Ship, 77.09%, and DTIL, 95.76%. Furthermore, AGNet demonstrates robustness against additive colored noise and low cutoff frequency. The authors conduct experiments to evaluate the performance of AGNet under different conditions. Specifically, they test the system on low signal-to-noise ratio and low cutoff frequency scenarios. The results show that AGNet outperforms traditional methods, such as MEL filter banks, in these challenging conditions. The learnable wavelet transform in AGNet allows the system to adapt to the input signal, resulting in improved recognition accuracy. The authors attribute the success of AGNet to its ability to learn and update parameters in a data-driven manner, reducing the need for manual parameter tuning. This end-to-end structure also simplifies the deployment process and reduces the possibility of module docking problems. Future work includes exploring the performance of adaptive learning on more complex data or tasks, such as setting more learnable parameters in the time-frequency feature extraction step. The authors also acknowledge the limitations of their work, including the potential challenges posed by low-dimensional features with less information. The paper provides a comprehensive review of related literature, citing works on underwater acoustic signal processing, wavelet transforms, and deep learning techniques. The authors also provide detailed information on their experimental setup, including the datasets used and the evaluation metrics employed. In conclusion, AGNet offers a promising solution for ship-radiated noise recognition, demonstrating robustness and adaptability in various scenarios. The system's ability to learn and update parameters in a data-driven manner reduces the need for manual intervention, making it a valuable contribution to the field of underwater acoustic signal processing. This paper presents a novel approach to adaptive ship-radiated noise recognition using a learnable fine-grained wavelet transform. The authors have developed a deep learning model that integrates auditory-like mechanisms and two-dimensional feature fusion for enhanced underwater target recognition. They utilize techniques such as convolutional neural networks, CNNs, auditory-inspired time-frequency analysis, and feature extraction methods like MEL-frequency Kepstrom coefficients to improve the accuracy of ship-type classification. The proposed model is trained on an underwater vessel noise database, demonstrating improved performance compared to traditional methods. The study also discusses various denoising techniques, including wavelet denoising with independent component analysis, ICA, and their applications in ship-radiated noise recognition. Furthermore, the paper explores different time-frequency analysis techniques, such as short-time Fourier transform, continuous wavelet transform, and Stockwell transform, to analyze underwater acoustic signals. In addition, the authors review several neural network architectures, including the convolutional block attention module, CBAM, which they find effective in enhancing feature extraction and classification. They also highlight the importance of data augmentation and the use of atom optimization algorithm for stochastic optimization in their model training process. The paper concludes by emphasizing the potential of deep learning techniques in underwater acoustic signal processing and target recognition. It suggests that future research could focus on developing more robust models capable of handling diverse underwater environments and conditions. The work contributes to the advancement of underwater surveillance and communication systems, providing insights into the application of machine learning and signal processing techniques in this domain.